Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 2 of Arrow 4080 Finite Elements. Today we're going to be going and looking at the basis for the finite element method. We're going to focus on one of the simplest spring elements, and then we're going to look at how this method plays out. Let's take a look at how it works. So if we kind of go back and think a bit about what you already know, we can focus on a spring element, right? If we have a spring element, a single spring element would look like this figure to the left. If we have multiple spring elements, they might look something like what's to the right. We might have some kind of coordinate system. Now, if we have a single spring element, then our coordinate system is basically going to be aligned. Our local coordinate system, or the coordinate system for that spring itself, will generally coincide with our global coordinate system, or the coordinate system for the whole model. If we have multiple springs, then we can't use the same coordinate system or local coordinate system for all the elements, so we'll tend to use a global coordinate system. We'll need to be able to talk the language of what is the local coordinate system for each and every element, as well as what is the global coordinate system for the entire model. In this picture to the right, we see while each element may have its own local coordinate system moving from one node to the other node in an x direction, a one-dimensional element, the global coordinate system could be aligned with any of these or none of these, as shown here. With that idea in mind, we can recall that when we do have a spring, then the displacements are related to the forces through the spring constant. So if we know the spring constant of the spring, usually it's just K, then we have the forces are equal to that spring constant times the displacement. Now if we have a single spring, we have a single displacement. But this principle is true for structures made of multiple things as well as just a single thing. So here we're going to see this lowercase f means it's the force in the element, and a lowercase k is a spring constant for the element, and our displacement is the displacement in the local coordinate system of the element. We're going to tend to use brackets for matrices, and we're going to tend to use braces, these braces for matrices that are just vectors. There's just a row or a column of data. Okay? All right, so we can actually write this in more detail. If we have, so while this first equation is valid both for a single element and multiple elements, if we actually had multiple elements like the one up at the right, what we would do is we would get an equation for each and every spring. The force in each and every spring will be the spring constant of that spring times its displacement. And if we look at that same equation where we look at the nodes, like node 1, node 2, node 3, then we could talk about the force at each node and each element is going to be a function of the displacements at that node times whatever elemental stiffnesses affect the node. For example, if we have a node here and we have one element, then actually only one spring constant will show up at that node because only that one element will affect the node. But if we have two elements springing out of that node, then both stiffnesses will affect the node because any movement of the node will cause forces in both elements. So we see, if we look at that column to the right, displacement 1 at node 1, displacement at node 2, displacement at node 3, these displacements, and here we're talking about a linear system, are a function of all the elements that attach to the node. Any elements in the model that don't attach to the node will have a zero stiffness for affecting that node. They may have a stiffness to affect other nodes. Okay? With these ideas in mind, we're ready to move forward in our discussion. If we did have this written correctly, we can now solve this system of equations, impose any boundary conditions, and then solve this system of equations to calculate the forces from the displacements or the displacements from the forces. Okay? This is a gross simplification. We're going to break this down in more detail as we move forward. So now there's a number of different methods for doing finite elements. The direct stiffness matrix that's shown here is one where we're going to assemble a global coordinate, a global stiffness matrix, and then impose our boundary conditions and our external forces and solve. Okay, this is very direct. Sometimes we need higher methods to do this. Our boundary conditions, we're going to have to not only calculate what is the stiffness matrix of each and every element, we're also going to have to then assemble the stiffness matrices of all the elements into a global stiffness matrix. And then we're going to be relating forces to displacements as a function of these stiffnesses. And in order to solve these, we're going to need to impose our boundary conditions, just like we did when we were calculating the deflection of beams in arrow 3261. We saw that each and every constraint beyond the ones required, the first three, added a unknown that we couldn't solve for with statics. But when we accounted for the displacement and then we integrated and plugged in our boundary conditions, we were able to solve. In the same way, to solve our global stiffness matrix, we're going to have to impose our boundary conditions so that all the superfluous constraints can be solved by taking advantage of what the constraint is on the structure. Okay? So we're going to be imposing these boundary conditions and blah, blah, blah. Okay? All right. So there are two kinds of boundary conditions. You probably remember back to your calculus classes. Homogeneous constraints, which are the easy ones. Whenever we have a structure where the nodes are completely restrained from moving in certain directions, that's called homogeneous constraint because the displacement is going to zero, or the solution of that equation is zero. Therefore, it's a homogeneous equation. There are easier methods generally to solve those kind of problems. A non-homogeneous boundary condition is one where, let's say we have the node is not constrained from moving, but it is maybe got an enforced displacement, or it's only allowed to move a certain amount. This makes the problem a little bit harder. If you remember back to arrow 3261, you'll remember our thermal problems, where if we just have a piece of structure lying on a table with no constraints, it's really easy to determine the thermal displacements. But if you completely restrained it, it's not too much harder. But if you partially restrain it, you only allow it to move a certain amount, it gets much harder. Or if you take a structure with no thermal, but you just pull on the node, impose a constraint, it can be challenging to figure out what all the internal forces are. The same thing is true here, but this is just going to set our problem either into a homogeneous problem, which will be a little bit easier, or a non-homogeneous problem, which will be a little bit harder. Got that? All right, so let's take a look at our 1D spring element. Once again, we're going to keep our elements simple in this class. Our goal with this class is just to understand the method and how it works. For the simplest elements is actually good enough because we're not going to be using this method in industry to solve these problems. We've got computer programs that do this, and that's a part of this class also, is learning some of those major computer codes. But by learning how it works for some of the simpler elements, we're going to gain insight into the process that has the opportunity to make us better finite element modelers and make a better chance of us getting good results that are meaningful rather than just a bunch of nonsense. Okay? So we're going to focus on the 1D spring element. So let's take a look at this spring right here. Here we have a spring, and it's going to be critical that you pay close attention to nomenclature in this class. If you are a careless person, you're going to have to take a special care. If you aren't careful with the nomenclature, you will get completely wrong answers, and that will obviously affect your grade. Okay? Let's take a look at this spring. We have a single spring here. We can see at the left, let's just take a look. We got one spring, so we have one spring constant. That's the element spring constant. There's only one element. We have two nodes. That spring is attaching two nodes. Now, it is possible to have zero-length springs in finite elements. We'll talk about those a little bit later. We have a spring constant. We have two nodes. The spring is attaching two nodes, and you'll notice the spring constant is only affecting the x direction. If we look at the local x direction, since we have a single element, the local and global coordinate system are the same, and our x is aligned this way, and nothing else really matters, because the only direction this spring is applying stiffness is in the x direction, and no other directions for this particular simple spring. So we have a spring constant, we have a length of that spring. At node 1, we can expect we may have a force. At node 2, we may have a force. We're going to use the nomenclature little f, which means it's the elemental force, in element 1, or excuse me, at node 1, that's a little subscript 1, in the x direction. You'll notice it's pointing to the right. That's because you'll see that our x coordinate system, the coordinate system for our x, is oriented to the right, and so we're going to show a positive force is not one that's tension necessarily, it's one that's aimed in the x direction. This is a critical little element, a simple element, but a critical element to understanding what we're going to be doing. So at node 1, we have a force at node 1 in the x from element 1, and at node 2, we have a force in the x from element 1 again. Okay, you see that? All right. You'll notice both of those are shown in the positive direction, so if we get a positive result, we're going to have a positive. If we get a negative result at node 1 will mean tension. A negative result at node 2 will mean compression. You see how that works? Okay. With that nomenclature in mind, we then can talk about our points. Our 2 points, we're going to call them nodes. Actually, Strudel, you calls them nodes. ANSYS, I don't recall. I think it calls them nodes as well. Nastran, when we do our Nastran models, we'll call them grids, G-R-I-Ds, okay? But that's just different terms to refer to those points. So we're going to call those nodes. At F1x and F2x are the forces at those two grid points or nodes in the x direction. Once again, we're talking the global x. These are local forces, which means we're in the local coordinate system. In this particular case, our local and global coordinate system are the same because there's no need for a different coordinate system. We could say that our displacements are u1 and u2. Actually, it looks like mu1 and mu2, and I'm not quite sure why that is. It's actually u1 and u2. I will fix this later. Maybe I just pulled this from their slides. That's a typo from the text. But ignore the mu. That's a u1 and u2 are the displacements, the local displacements in the x direction at each of those nodes. K is our spring constant. We only have one element, so we only have one spring constant. That's the stiffness of the spring, right? And L is our distance between the nodes. Okay. So if we go on with that idealization, we now can look at this. We see, okay, we've got our spring with a spring constant. We've got node 1 and node 2. If we define the displacement at node 1 as positive in the positive x direction, and at node 2 positive in the positive direction, you see that? And if we look at, well, let's call these force at each end T, let's call it a tension force, we'll see the displacement of the total element is U2 minus U1. That's not mu, that's a U. U2 minus U1 is the total displacement of the spring. And the tension force will be just that spring constant of the spring times that displacement. If U2 is larger than U1, we're going to get a positive displacement, which will cause a tension. If U2 is smaller than U1, that will give us a negative displacement. That will give us a negative compression in the rod, in the spring. Okay, so delta is just the total deformation of that element in this particular case. We can then combine these equations to say, okay, that the force, the tension force, is just K times U2 minus U1. We could have defined T, that force, as being compressive, and then it would have been U1 minus U2. But we're going to stick with this nomenclature. So the tensile force is equal to the spring constant of the element times the difference in displacement between element 2 and element 1. If these both displace to the right by 1 unit, then the displacement of the actual element is 0. It doesn't change length. Therefore, that's going to give us a 0 force. But if 1 is held and 2 moves, then the difference is just a movement of 2. That's the delta, and then we're going to get a tension force. If 1 moves and 2 doesn't move, that will cause a compression. It'll give us a negative displacement that would cause a compression. You see how that works? Okay. All right, so if we basically perform a force balance, we see that the force in the x direction in element 1, or excuse me, at node 1, the local force at node 1 in the x direction is just negative t. Remember? Because if we have a tension, then that tension is acting in the negative local or global x direction. And at node 2, if we have a tension, that's going to give us a positive force. Now, then if we take those two items, that force in the x at 1 and the force in the x at 2, and we can combine them in the same way. We can say, well, the force at 1 is just k times u1 minus u2, and the force in 2 is just k times u2 minus u1. Okay? Now we can, this is two equations that both must be satisfied, so we can actually write a system of equations. We have two simultaneous equations. We can write it in matrix form. F1x is equal to k u1 minus k u2. F2x is equal to minus k u1 plus k u2. That's two separate equations. Both must be fulfilled. If we solve this system of equations, we can solve the system. If we know what our displacements are, we can calculate our elemental forces. If we know what our elemental forces are, we can calculate our displacements. Got that? Okay. So if we have an element, let's say we have that spring element, a single spring element is going to have a stiffness. And that stiffness will affect both nodes that the element is attached to. It's going to affect node 1 and node 2. We're going to look at how this works. But you can start looking at this now and seeing that this element, we're going to look at this further before. This is the stiffness matrix of the element, of a certain element, okay? And if we look at this, we say, okay, for each element, we have node 1 and node 2. So if we look at this, we say, okay, this is node 1 and this is node 1, this is node 2 and this is node 2. Therefore, 1, 1, this is at node 1, 2, 2 is at node 2. This is the stiffness affecting 1 from 1, and this is the stiffness of 2 affecting 1. Okay? So if we look at this, we can say, okay, we're going to put the spring constant here and here, because that spring constant has a direct effect on each of these nodes, and it has a negative effect on these other nodes. So we're going to populate this matrix 1, 2, 1, 2, and we're just going to put our k. Here is positive, here is negative. You see that? So if you aren't totally clear, that's okay, because we're going to keep doing this. Once again, taking a look at this, we've got element 1. If we look at our node, this is element 1. We've got, if we call this node 1, node 2, we're going to put our k here and here, and our negative k here and here. This is called the elemental stiffness matrix. The stiffness matrix of the element. And we're going to be using this nomenclature. We're going to put the element number in parentheses. Okay? So this is a local stiffness matrix because it's for the element. It's symmetric. You can see that it's symmetric. It's square and it's singular, which means our determinant of that thing is going to be 0. This allows us to solve this. This is the basic process for determining the stiffness matrix of any element. Of course, this is for the spring. All right? Okay. With those ideas, let's move forward. All right. So let's take a look. Let's extend this further. Let's say, okay, well, we almost never deal with a single spring. We could have solved that by hand. Actually, you can solve most of this by hand as it gets increasingly hard with more elements. Let's start with a simple one. Let's say we have node 1, we have 2 springs, and they're both aligned in the same coordinate system. So we just got X direction. So the stiffness is only affecting the movement of the grids or the nodes in the X direction. Element 1 goes, spring 1 goes from node 1 to node 3, and the second spring goes from 3 to 2. Let's say that we're fixed or pinned at the left end, and we have external forces applied at grids 3 and nodes 2. Remember, grid and node are interchangeable word, okay, or points. Usually points, the word point is used when we're talking about CAD models, just drawing things. Whenever we start talking about finite elements, we're usually using the words either nodes or grids, okay? Grids is the term used by Nastran, nodes is the term used more generally. All right, we see that node 1 is fixed, and we have axial loads applied at 3 and 2, okay? So we're going to go ahead and look. We can say, okay, from what we already learned, we're going to have a stiffness matrix for each of these springs. That part's simple. But what we're going to see here now is we're going to learn how to assemble the stiffness matrix for the entire structure. Remember, last slide we saw a local stiffness matrix, a stiffness matrix for a single element. We're going to need those for each and every element in our model. Then we're going to have to learn how to construct our global stiffness matrix, where we're looking and taking each element stiffness matrix and putting it in the places it belongs in the global stiffness until we have a stiffness matrix for our entire structure. Okay? Stand by. Stay with me. All right. So our local stiffness matrices, right here we're seeing again, we've got for element 1 goes from node 1 to node 3, and so actually we can, and we're going to see this again, so we can say, okay, element 1, we're going from 1 to 3, from 1 to 3. So we have F at node 1 in the X, F at node 3 in the X, both of them for element 1. We've got the displacement at node 1 from element 1, or for element 1, and the displacement at node 3 for element 1. For the second element, we now have, you'll notice these guys up here are all for the element. So this is the force at 3, because this one is going from 3 to 2. This one is going from 1 to 3. Remember that? That's why we're going 1 to 3, 1 to 3. And this is going 3 to 2, 3 to 2. Okay? Sticking with the same. Remember, so we have, this is our total system. This is 1, this is 3, and this is 2. Okay? So these are the forces here. We've got a force here, and so on. You got that? This is for element 2, this is for element 2. Okay, but if we look at this, we say, wait a minute. The displacement here, U, at 3 is it's like a global constant, right? If this node moves at all, if it moves this way, then both element 1 and element 2 see the exact same displacement. So that's where we see that the displacement in 1 at 3 and the displacement at 3 in 2 has got to be the same, and we can just call it the displacement at 3. You see that? So this is really U1, and this is really U3, this is really U3, and this is really U2. So really we see, and these are called continuity or compatibility constraints. Okay? So imposing that, we recognize that that's true. Okay? Once again, we talked about these little notes. If you didn't understand what I said before, take a look here. So once again, we've got F1x1. That means we've got a force at node 1. It's an elemental force because it's a lowercase f. We're going to use a big F for external forces. This is at node 1 in the x direction, and this is in element 1. If this were a 2, that would mean in element 2. Okay? That kind of thing. All right. So now that we've done that, we can take a look at the free body diagram, the exploded free body diagram. We got some practice in Arrow 3271 with exploded free body diagrams. Actually, we did that node method that we learned in statics, where we took a truss and we broke it all apart and pulled the nodes of elements, each little rod away from the points. That was an exploded free body diagram that was very helpful for solving those kind of problems, especially using like the node method. Okay. So we can see then we have element 1, right, and element 2. Element 1 goes from 1 to 3, and element 2 goes from 3 to 2. 1 to 3, 3 to 2. Okay. We've got a spring constant for 1. We call that K1. We've got a spring constant for 2. We've got a force. F1x is in the positive direction. If it's positive, it's aiming this way, which would be compressive. And at node 3, a positive force means it's tension for this. Okay? In the same way, actually at that node is also going to have, if we have an external force at node 1, then it better equal, if we sum our forces in the joints, remember the method of joints from statics? If we sum our forces in the x direction, they have to be equal to 0. Therefore, we see if we have an external load, it better be equal to the load in this piece. If we have a positive, which means acting in the positive direction, that's going to cause a resisting load that's equal and opposite, which means this is going to get the exact same. In this case, these are equal, right? The external force at node 1 in the x better equal the force in element 1, since element 1 is the only thing attaching to that node. Now, if there were multiple elements, then the external force would be the summation of those. We see at the other end, we have the force in element 1 at node 3 in the x direction. And looking at this joint, this is equal and opposite. Whatever this is going to be equal and opposite. That's got to be the same. And then we had also a positive force at node 3 in the x direction on 2. And equal and opposite, that's affecting this, just like the method of joints. Therefore, we see that any external force F3x is going to be equal to, right, F3x minus F3x in 1 minus, or excuse me, yes, minus F3x in 2 has got to be equal to 0, so we get this equation here when we bring both of these terms to the other side, okay? And so on. F1x has got to be F1x minus F1x, little f1x in the element 1, that's got to be equal to 0, and these have to be the same also. These are called equilibrium equations because we applied equilibrium to the structure. So we saw the compatibility equations, which basically looked and said, look, if this node moves, both elements know that node is moving the same for both elements. That's the compatibility or continuity equations. Okay? Here we're saying we're imposing equilibrium, which means we're summing the forces and moments equal to 0, in this case just forces, and this is where we get these other relations. Okay? These tools of our trade, this is why we need to have mastered statics and strength 1, and it will help if you master strength 2, although that's not actually critical for this class. May make it a little easier. Then this is what we're doing here. That make sense? Let's move on. Okay. Now we can combine them. We can combine all of our local matrices into a global matrix. And we're going to look at this in depth on the next slide. But remember, if we look at the whole system, we're going to have external force at node 1, external force at node 2, external force at node 3. See that? This is going to be node 1, node 2, node 3, node 1, node 2, node 3. We're going to put these together and look at which, remember we have 3 springs, each has a stiffness matrix, and all of these are going to feed into our global stiffness matrix. We're going to be looking, this one went from 1 to 3, this one went from, oh, excuse me, here's only 2. 2 springs. This one went from 3 to 2, and both of these feed into our global stiffness matrix. So these are our external forces in the global. This is our displacements in the global. And these two stiffnesses feed into the global matrix. We're going to see how that works out on the next slide. Once we have it at this stage, we're almost ready to start solving this. So F is our global nodal forces. Our global forces at each node. In our case, we had a spring structure like this. So we could talk about F here, F at 1 in the x direction, F at 3 in the x direction, F at 2 in the x direction. That's what these forces are. If these forces are aimed in the positive direction, they'll be positive. If they're aimed in the negative direction, it'll be negative. It has nothing to do with tension and compression. It has to do with our global coordinate system. Okay? D is our displacement matrix. Okay, in this case we're using U. We could call this whole little vector D. We could call this whole little vector F. This whole little vector D. We're using U's for the individual ones, but D is what we could also call that. Okay? And K, now you'll notice we used a lowercase k for our stiffness matrix of our elements. We're going to use an uppercase K when we're talking about the stiffness matrix of the global stiffness matrix. Okay? You got all that? All right. Don't worry. We're going to actually break this down step by step on, I believe, the next slide. Here we go. All right, before we do that, we're going to take a look at our spring sign convention. Once again, we need to define a spring sign convention. The local sign convention for the spring is going to be aligned along the spring from element 1, from node 1 to node 2. Let's think about that for a minute. Let's say we have a spring that goes from node 1 to node 2. Okay? That means the X is going to go this way. Let's say we have a spring that goes from node 2 to node 1. Well, once again, the lower node is 1 going toward 2. This is our positive X. So with springs, we're saying, okay, what is the first node in the call out and what is the second node? Now, if we call out the spring going from 1 to 2, if we call out our spring going from 1 to 2, then this is our coordinate system. If we call out our spring going from 2 to 1, then this is our coordinate system. Do you see that? This is a local coordinate system. If we have a spring going from 4 to 9, then this is our coordinate system. If we call it out going from 9 to 4, then this is our coordinate system. Do you see that? Okay. All right, so here's our basic relation. F equals kx, right? F equals k times the displacement, which we've been calling U for the local displacements, okay? That's our basic relation, and this is on the nodal level. So we have once again, this is a single element, so we've got F at 1 in the x, F at 2 in the x. Our spring constant, that means this is element 1, 2, 1, 2. That means we put a positive k, negative k, and this is going from element 1 to element 2. Now that's because we label these 1. If this was 2 and 5, that would be 2 and 5. If this was 3 and 9, that would be 3 and 9. If that was 9 and 3, it would be 9 and 3. You got that? Okay. Our nodal forces then, that's these guys. Our nodal displacements are these guys here, and our stiffness matrix looks like that for that particular element. You got all that? Okay. With that said, we're ready to build more. So here's the final element method. We're going to look at the final element method twice. We're going to look at it for homogeneous constraints where something is fixed, and we're going to look at it for non-homogeneous constraints when something is got a constrained displacement or enforced displacement. Okay? Let's start with the homogeneous constraints first. All right. So let's say we have this little model here. It looks like we have two springs. We have spring 1 goes from 1 to 3. Spring 2 goes from 3 to 2. It's element 1, element 2. Goes from 1 to 3, 3 to 2. We've got K1, K2. We've got a constraint where it looks like we're fixed at point 1. We have an external force at node 3, it looks like, and we have an external force at node 2. Okay, that means, taking a look at this, we can see that we actually have a force at node 1. We just don't know what it is. It's because of that constraint. All right? Okay. So let's draw a free body diagram. We've got node element 1 and element 2. We've got the forces. Remember, if we look at this element, we see that the forces on element 1 defined in the positive direction, defined in the positive direction. This is at 1 and at 3 in element 1. Okay? On the element 2, we've got at element 2 at node 3 and node 2, both aimed in the positive x direction, right? The positive x, that's for element 2. We see at node 2, we have this equal and opposite force, and we also have any external force. That might be 0, it might be something. At node 3, we have forces from each element, and we have this external force, which may or may not be 0. At node 1, we have the force from element 1 and the force from the constraint. That's our exploded free body diagram that we discussed before. Okay. Now we're ready to write our global stiffness matrix. If we could write this, we could get the forces in each. Remember, the capital F means the force, the global force or the external force at nodes 1, 2, and 3. We're going to need the global stiffness matrix to get that, and we're going to need to do that, we're going to need the displacements at those 3. So how do we populate our global stiffness matrix? We talked about it briefly before. Now we're going to go into the details. Stand by. So we have this free body diagram. Remember, we just did that. And we have, this is our element 1 relation, right? Element 1 has K1. It's got a force in element 1 at node 1 and a force in element 1 at node 3. And it affects global displacements at 1 and 3. For element 2, we have the stiffness matrix of element 2. At node 3 and node 2, we have forces from that element, and these forces affect the displacements at node 3 and node 2. Okay, so if we want to populate our global stiffness matrix, what we're going to do is take a look at what nodes apply to each, and this is a critical step. It's simple, but it's critical. Okay, this is the displacement 1, this is displacement 1, right? We could put, if we just lay out our displacements 1, 2, 3, right, on the rows and the columns, you see how we did that? Then we're going to do the same thing. Once we've laid this out, we could, how we identify these. Now, we don't actually have to make this incremental 1, 2, 3. This could be 1, 5, 7. But whatever we do, we need to keep consistent nomenclature with our elements. So let's say we're going to populate our global stiffness matrix 1, 2, 3, 1, 2, 3, right? These two have to be the same. Okay. With that said, we see element 1 is going from 1 to 3. And element 2 is going from 3 to 2. Notice it's not going from 2 to 3. It's going from 3 to 2 based on our, remember, our global coordinate system. If we look right up here, let me just write this out. Remember, element 2, well, let's do this. Element 1 went from 1 to 3, and this was what we called x global. Element 2 went from 3 to 2, and this was called, right? Therefore, we have to put this first, and then this first, and then this first, and then this first, and this. You see how that works? Okay, this is critical. So we've got the same thing. We're going moving from left to right according to our coordinate system. Our coordinate system was called out to be this is positive x. Therefore, this has got to be 1, right? And we're constructing 1, 2, 3, 1, 2, 3. That's nice and simple. We could actually jumble those, but it actually will get harder to keep track of everything. This is just simply the nomenclature that's familiar, 1, 2, 3, 1, 2, 3. But then when we look at what those elements affect, we've got to take into account our global system and how that element is oriented relative to our global system, right? This could, if we had a spring 9 to 3, then we'd have another term, okay? All right. Okay, with that said, we're now ready to take a look. Let's look at this stiffness matrix. We see that this stiffness matrix, we call this green, that's going to affect this term, right? It's going to affect node 1 and it's going to affect node 3. Therefore, we see this term here at 1, 1 goes into 1, 1. This term here at 1, 3 goes into 1, 3. This term here from 3, 1 goes into 3, 1 down here. And, excuse me, oh, I skipped over a step. So we see this displacement now. We saw this F1x. Let me go ahead and get this all in here. All right, and then I'm going to bring it like this. So what we see here is this is at node 1, so this guy is going to go into here. Now, it might not be all of what's there, but this guy is going to be here. So we're going to have an F1x here. This guy is 1, 1. So 1, 1, this is going to go into here. This guy is 1, 3. So this is going to go into 1, 3. And this guy is at node 1, which will go here. You see that? Everything else is 0 right now. Okay. Then we're going to look at the second row. Now we're going to say, okay, this guy here is going to go into node 3. This guy here is going to go into 3, 1. 3, 1. This guy here is going to go into 3, 3. And this guy here is going to be 3. You see that? Let's take a look at how that works. Let me erase the ink on the slide. And we then see that's this. This guy goes down there, this guy goes down there, and this guy goes down there. You see how that works? Now let's see how the second element populates the global stiffness matrix. If we color this one, this orangish color, we're going to see our first term goes here. What that means is this term here is at node 3, that goes there, the force at 3. Okay? The second term, this is, right? This term here is 3, 3. So this term is going to come down here to 3, 3. The next term, this is 3, 2. So that's going to go to 3, 2. Okay? Then we're going to see our displacement at 3 is going to come into here. Okay? If we continue, we see now F2 goes here, right? And we see 2, 3, 2, 3 goes there, and 2, 2 goes here. D2 goes there. That's how that works. Okay? So with that said, we can look at this and say, oh, okay, so that means the only F1 was coming from element 1. So this global force at 1 in the X is just the local F1 in the X. And at node 2 at the far end, we see the only one of these that goes into node 2 is this one. That means F2 in the X, the global, is just the element 2's local F2x. We see though at node 3, the force at 3 is affected by both the force in 1 at 3 and the force in 2 at 3. So we see that F3x is the summation of these two. We see the only one of these two stiffness matrix affecting the 1,1 term is this term right here. We see at node 2, we see at L-02, 1,2, the only thing affecting it. There's nothing affecting it, right? If we look here, there's nothing tying 1 to node 2. Node 1, element 1 is not attached to 2, therefore there's no term, so that's 0. We see at node 3, all we see is this term right here, right? And then looking at the second guy, and so on. So we see, taking a look at which ones, you'll see here, this is only affected by 1, this is only affected by 1, this is the global one, this is the local one as well. Here we see that's only from 2. This is not affected by either, this is not affected by either. This one is only from 2, this is only from 2, and this is only from 2. Then we look at 3, that node between them, the force at 3, the external force, is affected by both element 1 and 2. And the stiffness matrix is only affected by 1, the first term. The second one's only affected by 2. The third term is affected by both at node 3. And then the displacement at 3 is affected by both. That gives us this stiffness matrix here. This is called the global stiffness matrix now. What we see is the global displacements as a function of the global stiffness matrix and the global external forces. External forces, global stiffness matrix, global displacements. You see that? That's the key to the method. Let's take a look at this further. So this was U, we were calling this before U at 1 in the X, we were calling this U at 3 in the X, we're calling this U at 3 in the X, we're calling this U at 2 in the X. Okay, and here's some notes of what we just said. All right, now we have the global stiffness matrix. We now have a system of equations, a global system of equations. Remember, this is our model, and now we're going to try and impose our boundary conditions. This is like solving for the constants of integration when we were solving transverse beams in arrow 3261. This is our global, in fact, actually just this little piece right here, this matrix here. This is our global stiffness matrix. Right? This is our external forces. This is our global displacements. Got that? External forces, global stiffness matrix, global displacements. Okay, that's the equation we developed on the last slide. All right. So we're going to impose our boundary conditions. So let's take a look at our global stiffness matrix again. We see that the boundary condition at 1 is 0. Okay? The displacement at 1 has to be 0. What that means is whenever we have a 0 there, we can eliminate that constraint. It eliminates the row and it eliminates the column. Okay? So we eliminate that row of 1 and we eliminate the column of 1. We've got to be very, very careful to eliminate the correct row. That is the only constraint. What that leaves us is a reduced stiffness matrix. You see now we just have 2 forces and 4 stiffnesses to get our 2 displacements. If we have the displacements, we can plug them in and solve for the forces. And if we have the forces, we can solve the system of equations for the displacements. Okay? Now, we can then, if we have our displacements, generally that's what we're going to have, we'll then solve this system of equations. If we have our displacements, we solve for the forces. If we have the external forces, we solve the displacements. That's what we have in this case. Look, at F2 we have an external force. At F3 we have an external force. And we can then solve the inverse of this system of equations. This is where it'll be really helpful and actually nearly required if you have a calculator that can solve systems of equations. There's already a lot of work in finite elements just setting up the right matrix. There's no reason for you to throw away points when you're trying to solve the system of equations, especially if we get into larger matrices. You're probably not going to be able to do it correctly not in the kind of time pressure we're going to have. You need a calculator that can solve systems of equations. And if you do that, you can plug in your external forces. They may have a value, they may be 0, and your stiffness matrix, your global stiffness matrix, once you've constructed that correctly, and solve the displacements, okay? Once we have the displacements, we then plug those displacements back in. We're going to go back to that original equation, which you see down here, and we're going to plug those in. Let's take a look at this. So once again, this was our set of equations. We came here and we imposed our boundary conditions. What that means is we saw that this displacement was 0, so we eliminated the row and the corresponding column. Remember, this was 1, 2, 3, this was 1, 2, 3. So if we knock out the one row, we can knock out the one column. That left us a reduced system, which we see right here, and we show right there. We then solve the system equations. We don't know what these displacements are. We do know these two forces. Whatever these two external forces are, we have those. We plug those in, and we plug in whatever these values are that we just calculated, and we solve the system equation using our calculator to get these two guys. We then plug these two guys in right here, and we already knew that this was 0. We also have these forces, right? We have all the displacements, and we actually have these two forces. We don't know what this force is. So we can now just multiply this out. This equation, this equals this times this plus this times this plus this times this. So what we're going to do is, using these displacements and this global stiffness matrix, we're going to solve this. Now you'll notice when we do this, we're going to get these two values, which we already used. They better be the same or else something's wrong. This is the guy that's changed. This is the guy that we didn't know before, and now we know by solving the system of equations. Okay? So step 1 is constructing global stiffness matrix. Step 2 is imposing boundary conditions and getting rid of anything that we don't need. Step 3 is solving the reduced system for the global displacements. Step 4 is plugging those global displacements, all of them, the ones we eliminated and the ones we determined, into our global stiffness matrix again to calculate whichever forces we didn't know. We can check the ones that we already knew, make sure they didn't change, otherwise something's wrong, and get the ones we don't know. And then we can go and get the next step, which we're going to look at next, which is where we then take those external forces and the global displacements to calculate our elemental forces. That we do that by going back to those two elemental stiffness matrices. That means we plug in D1 and D3 with K1 to get our forces at each end. These are our internal forces. This is the internal force in 1 at node 1 and at node 3. Now once again, the global forces are a function of our coordinate system. So positive means the same in the positive direction, negative means the same to the negative direction. Our local forces also mean positive is in the positive direction, negative is in the negative direction. Therefore, a positive value could be tension or compression. A positive value in this case at node 1 means the local force is going in the positive direction. That's actually a compression. A negative value will mean it's in tension. At node 3, a positive value means tension, and a negative value means compression, and so on. Okay? That's basically the method. That is the power of the final method, shown on probably the simplest element we can, a single spring with a couple springs acting together. Got that? That's for homogeneous constraints. Now let's take this a step further and look at non-homogeneous constraints. Are you ready? Hang on to your seats. Okay. So if we have a similar problem, this looks similar. We've got two springs again going from 1 to 3 and 3 to 2, and now we have an enforced displacement. I'm going to move a little faster on the things we've already done and a little slower on the things we haven't done. Okay? This time we have an enforced displacement. Bummer. This makes it more complicated. We're going to start out with a free body diagram. As we did before, we see that we're going to get our compatibility and our equilibrium equations the same way. This is the same free body diagram we had before. And now we can we're going to construct our global stiffness matrix. We're going to calculate that in the same way as before. Okay? Which means we're going to get the stiffness matrix for each and every element, being careful to take care of where the nodes are. And then we're going to construct, it's called assembling. We're going to assemble our global stiffness matrix from those local element stiffness matrices. Once we've done that, we're going to say, okay, the force at 1, external force at 1 in the x, external force at 2 in the x, external force at 3 in the x is going to be equal to that global stiffness matrix times the global displacement at 1, 2, and 3. Okay? This is all the same as before. All right, let's go into the stuff that's different. The difference is we now have an enforced displacement. Okay, what that means is our displacement at 1 is no longer 0. We can't just eliminate it. But we need to eliminate it. So we're actually going to, but we have to do more work to do so. Okay? So let's take a look at this a minute. So we have this enforced displacement at 1. It's equal to delta, we'll call it. Okay. What that means is we can't just eliminate this first row, but we really need to. Now, if we look at our stiffness matrix, we see that actually the force at 2 is not coupled with the force at 1. It's not using that first displacement. See, this first 0 means that's not being used. So what we need to do, we can eliminate row 1 if we can just alter our third equation to account for our first equation. That's what we're going to do, okay? Now what we need to do here is, if you look at this equation, you'll see that equation 2 has a 0 term. It has a 0 term right here. That means whatever's happening here doesn't affect it. But if we look at equation 3, we see it is coupled with that first displacement like this, because this term gets multiplied against it. Now, if we can rewrite this third equation to decouple the equation, then we can solve this system of equations. So that's what we're going to do. So what we're going to do is rearrange the third equation. We're going to do it like this. If we look at our third equation, we could see that f3x is equal to minus k1 times delta minus k2 times d2 plus k1 plus k2 times d3 equals 0. F3x equals all this. Okay. Now we can rearrange this. We can say, okay, F3x is equal to this minus k1 term, okay? And then for d2, we've just got this minus kd2 term, and then we've got this term right here. You see that? That's all we did. We just multiplied this guy out. Okay? So what we're going to do now is rearrange this equation by taking this. If we can bring this to the other side, then we can solve the equation. So that means f3x plus now k1 delta. We see this term is unchanged. That's actually supposed to be a negative. That's a typo. So this term goes right there, and this term goes right there. And now we have changed this last equation so that it's no longer decoupled. You'll notice that this term here is an unknown. Before we didn't know the force at 3, but now we may or may not have known it. But actually, by doing this, what we've done is we have lumped this into our unknown. So now we can solve this equation. So this force at 3 plus the k times the delta, this guy, lumping that together decouples this from the other equation. Let's take a look at how that works. So that means we can write our equation like this. we now have f1x is unchanged, f2x is unchanged, and f3 now is written this way. You'll notice now that the third equation is decoupled. Both these equations are decoupled, so neither one uses this term. Therefore, we can just focus on this stiffness matrix down here. Okay? That is our reduced stiffness matrix, and here's how it works. We can now eliminate that first row, not because it was equal to 0, but because it's now decoupled from the other two equations. And we can solve our reduced system of equations like this. So we plug in f2x and f3x plus k times delta with this part of the global stiffness matrix, or this is the reduced global stiffness matrix, and the displacements of those. We use this to solve for our displacements at 2 and 3. Once we have our displacements at 2 and 3, we then plug in delta and d2, delta 2, and the displacement at 3 to calculate our other force that we didn't know, the force at 1. Once we have the force at 1, we can use the forces that we now know, the external forces, and the global displacements to calculate the elemental forces in each element. And that's how this works. So if we just summarize our final method, here's a little summary of how it works. We're going to model our system with nodes and elements. We're going to determine the local stiffness matrix for each and every element in its local coordinate system. We're going to actually, this next step that's gray is transforming that into global coordinates. Now in this particular example, we don't have to do that because everything's just in a local, everything's already in the global coordinate system. So actually we'll learn about that later. Okay? We're going to assemble our global stiffness matrix. Now the summation doesn't mean we're adding all of our terms. It means we're taking care to figure out which terms go where, and then constructing our global stiffness matrix. Okay? Which means what we're going to do is we're going to take the stiffness matrix for each element and place it where it goes in the global stiffness matrix, added to any other local stiffness matrices that apply to that point. And then we're going to apply our boundary conditions to reduce the stiffness matrix. We're going to impose any boundary conditions and external forces. We're going to solve our system of equations for the unknowns after we've reduced our stiffness matrix. And this little r means we've reduced that stiffness matrix. That means the global displacements is equal to the global stiffness matrix, the inverse of that, of the reduced matrix, times the corresponding global forces. And then we're going to use those displacements with the other displacements that we already knew and just multiply by our stiffness, global stiffness matrix again to get any forces that global forces that we didn't have. Once we have those forces, we're going to take those and we're going to check any ones that we already knew, make sure they didn't change, otherwise something's wrong. And then for each element, we can use the global forces or external forces and the global stiffnesses to calculate the internal forces in each element, taking care to remember that the forces in the element are in the global coordinate system and then maybe needed to be transferred to assess whether it's in actually tension or compression for each element, okay? And then we're actually not going to do this grayed out step because we haven't learned how to do that. We'll be doing that soon, and this is just a placeholder for later learning. Got that? That's our approach. Let's look at some example problems. We already looked at a couple. In general, now let's look at numeric numbers. Let's say we have a 3-spring structure. Okay? 3 springs. The first one's going from 1 to 3, next one's going from 3 to 4, next one's going from 4 to 2. We've got stiffnesses for each of these, and we have constraints. We see our constraints at 1 and 2 are both 0. So we can go and get our local stiffness matrices, right? If element 1 has a spring constant of 1,000 pounds per inch, then that's going to populate a local matrix for element 1 of 1,000, 1,000, minus 1,000, 1,000, minus 1,000. You see that? Element 2 will be constructed in a similar manner, element 3. Now taking a look at this, remember element 1 goes from 1 to 2. Element 2 goes from 2 to 3. Element 3 goes from, element 1. Now taking a look at this, we see element 1 goes from 1 to 3. Element 2 goes from 3 to 4. Element 3 goes from 4 to 2. We then use those to construct our global stiffness matrix. Let's take a look at how this works. This is 1 to 3. 1 to 3. This is 3 to 4. This is 4 to 2. Okay, we see from 1 to 1, this is 1, 2, 3, 4. 1, 2, 3, 4. Okay, from 1 to 1, that's the only term, okay? At 1, 3, this is the only term, 1, 3. And at 3, 1, this is the only term. At 3, 4, we see we've got this term and this term. At, oh, excuse me, that's 3, 3. At 3, 3, 3, 3, we've got this term, and 3, 3 is this term. So 1,000 plus 2,000 is 3,000. You see that? At 3, 4, 3, 4, we have just this 2,000. 3, 4, right, as a negative 2,000. At 4, 3, there's not another 4, 3, so this guy is just 4, 3. At 4, 4, that's the only, at 4, 4 and 4, 4, so we have 2,000 plus 3,000, that goes here. We already did this one. At 4, 2, this guy here, we've got only this term. At 2, 4, 2, 4, we've got only that term, and at 2, 2, we've got only this term. Everything else is zeros. That's our global stiffness matrix. We then can put in our displacements. This is D1, D2, D3, D4. But we know that D1 is 0. And we know that D2 is 0. Right? That means we're going to have the reduced stiffness system there. Let's take a look at that. Right? Because 1 and 2 are 0. Now we can take the reduced matrix, which is this piece along with the global displacements. These two are 0. That's going to give us these two guys. We can then plug those in with our total global stiffness matrix to get the forces, the two forces that we don't know. Right? And then that's the two forces we don't know. And then we can use those global displacements and global forces in each stiffness matrix to get the elemental forces. Okay? You'll notice this is negative. That means it's going in the negative direction. That means it's in tension. This is positive. Means going in the positive direction. That's in tension. These better be, let's give the same kind of value, right? And so on. Okay? So if we show those results here, these are our forces. Those are our elemental forces. We can now draw a free body diagram from this information. At node 1, we have F1. It's going in the negative direction, and the F1 from element 1, which is also going in the negative direction, right? Since that element was going in the negative direction, that means the force on the node, that's the force in the element. So we'll notice here, once again, let me just remember, this force here means that this element here is going in the negative direction. That's F1x on element 1. And when we look at the node, then we're going to reverse the sign. So a negative here becomes a positive acting on the node. You see that? Okay. Now we can do the second one the same way, and then each of our elements. This 10,000 over 11 is just 909 in disguise, right? And so on. This 45,000 over 11 is just 4091 in disguise, and so on. See how that works? All right, let's look at another example. And this is for a similar problem. Once again, we have 3 springs. 4 springs and an enforced displacement. We can see at 1 we have a nice easy homogeneous constraint, but at 5 we have an enforced displacement. That makes it a little more challenging. We're going to have to change one of our equations to decouple the system. So we start off with the same process. We're going to get our local stiffness matrices for each. Those are pretty easy to get. Then we're going to construct our global stiffness matrix. That's pretty easy. Okay, let's just annotate this for a minute. This is element 1 is going, so if this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Element 1 was from 1 to 2, element 2 was from 2 to 3, 3 to 4, 4 to 5. Well, that's easy, okay? Now, if we look at this, we see element 1, we're going to be able to eliminate this directly because the displacement for that guy was 0. However, we're going to have to change the coupling. If we look at this and we say, okay, well at node 5, we're going to have to decouple our equations so we can solve it. So we're going to have to tweak one of our equations so that we can decouple one of these from our system of equations. Okay, so we're going to do that. We did that already. Let's erase this. And now we can look, and if we rearrange this guy, we can decouple this. Actually, this equation is, we can now rewrite that equation. We're going to have to use this here, F4. Rewriting that is equal to F4 minus negative K delta, and plug in that in, we get this guy and this guy. Make sense? That's how we do it. Okay. You're going to want to make sure you take enough time to solve the homework until you understand all of this. If you don't, you will for sure, we're going to be getting deeper and deeper very fast in this class. Make sure you can do both homogeneous and non-homogeneous equations using simple springs, all located, all aligned in the global coordinate system. That's what we need to know so far, and if you know that, you will be ready. Okay, so once again, we can handle, we're going to be able to calculate what the local stiffness matrix for any element. We're talking springs that are aligned in the global coordinate system. You can calculate the local stiffness matrix. You can assemble the global stiffness matrix. You can identify your constraints and which ones are 0 or which ones are enforced. For any 0 constraints, we're going to take advantage of the homogeneous system and eliminate those rows and columns from our matrix to get our reduced global stiffness matrix. If we have any enforced displacements, we're going to have to rewrite one of our equations to decouple our equation so we can reduce down one more, and then that will allow us to solve the reduced system. Once we have the reduced system, we're solved for our displacements for that reduced system, and then we'll use those displacements with the other known displacements to calculate what our forces are, unknown external forces. Once we have all external forces and all displacements in global coordinates, we can use those values in each of our local stiffness matrix system simultaneous sets of equations, or sets of equations, in order to solve for the local forces in the elements. Once we have that, we can draw our free body diagram and understand what the actual forces are in each element. And then we'll reduce stress analysis, which we'll talk about later. Make sense? Enjoy.